Hello everyone, I'm Kushal Lodha, a PhD student at Korea Astronomy and Space Science Institute. First, I'd like to thank organizers for giving me an opportunity to present today. I will be sharing our latest results from DESI DR2 dark energy supporting paper carried out as a part of the DESI DR2 release. This work is a result of collaborative effort with Rodrigo Calderon, William Matthewson, Aman Shafilo, and many other DESI colleagues. Let's begin with a simple question. What is dark energy? Dark energy is a mysterious component introduced to explain the late time acceleration of the universe. The concept of the dark energy dates back to Einstein, who introduced a constant representing a vacuum energy to counterbalance the gravity. This constant became a key part of the standard model lambda CDM after the discovery of the accelerating universe using type 1 supernovae back in 1998. So why lambda does not work? Although lambda CDM model has been largely successful, combining the recent observational data from different cosmic epochs such as the CMB, BAO, and the supernovae reveals the discrepancy in the amount of the dark energy needed to explain them. On the right, you can see the supernovae prefers a lower value of omega lambda, BAO much higher, and CMB somewhere in between these two. This suggests that dark energy may not be constant but evolving over time. We quantify this evolution using equation of state, which is ratio of pressure to the density. In standard lambda CDM model, this quantity is fixed at -1. To explore the redshift evolution, we use W0 WA parameterization that help us test whether dark energy is truly constant or evolving over time. Before we dive into the results for the evolving dark energy, it's important to keep in mind that we do not directly observe dark energy equation of state. What we measure are quantity like Hubble parameter h of z or the distances that depend on the integrals of h of z. Since h of z itself depend on the integral over w of z, any variation in the dark energy equation of states gets smoothened out. For example, type 1 supernovae gives us the measurement of luminosity distance, while baryon acoustic oscillation provide Hubble parameter and angular diameter distance as a function of redshift. The latest DESI data, when combined with CMB and supernovae, provide a tightest constraint on the dynamics of the dark energy. As can be seen on the right, the blue point indicates a lambda CDM, and depending upon which supernovae dataset we use, the significance of the deviation from cosmological constant ranges from 2.8 to 4.2 sigma. These results are fairly robust even when the Planck CMB anisotropies are replaced by ACT DR6 or a combination of both. We find that the deviations get a bit smaller, but there is still a noticeable departure for a simple cosmological constant. Here we show DESI plus Planck in blue, DESI plus ACT in orange, and DESI plus P ACT in the green dotted line. So we show DESI plus CMB, DESI plus CMB plus 3 different supernovae combinations, and you can see the results are fairly similar. To better understand this constraint, we convert these contours to a redshift evolution as shown on the left figure. Here I chose the blue contour with union 3 combination and convert them in as a function of redshift. On the top we have equation of state W of z, which goes from greater than -1 at low redshift to less than -1 at high redshift. This evolution is also reflected in the dark energy density FDE as a bump shown in the bottom plot. The peak of the density is around z equals to 0.1, that is marked with a solid gray line where W crosses -1, and the dashed gray line shows the matter dark energy equality. Next, we look at the deceleration parameter Q of z, which tells us how the rate of cosmic acceleration changes with redshift. The dotted vertical line around z equals to 0.8 marks the point when the universe transitions from deceleration to acceleration, much before matter dark energy equality at z equals to 0.4. Interestingly, the W0 WA model suggests that the universe has started accelerating earlier than predicted by lambda CDM. However, if we look at the present epoch, we see the hints that the rate of acceleration might actually be slowing down compared to lambda CDM. To test the robustness of this result, we start by considering several 2-parameter extensions with different functional form, as we can see in the plot. All 5 parameterizations capture similar trend at the low redshift. Despite the differences in the high Z behavior, they give identical or worse fit to the data, indicating data's inability to distinguish between these functional forms. Rather than restricting ourselves to two-parameter extension, we can ask how many dark energy parameters are needed. We introduce additional degree of freedom to see what kind of trends emerge. Here we use Chebyshev polynomial to expand W of z around -1. In the top right figure, I am showing our results for n equals to 3 with DESI plus CMB in orange and DESI plus CMB plus union 3 in blue, with black dashed line showing a prediction for lambda CDM. In addition to this, we also explore giving a similar freedom to dark energy density, which even allows for negative values. The result follows similar trend as W0 WA. We can repeat this exercise using different orders of Chebyshev expansion and plot how improvement in the delta chi-square relative to lambda CDM changes with number of free parameters. We find that the improvement in the fit tends to saturate around 2 for W of z and 3 for dark energy density. The dotted black line shows W0 WA improvement for comparison. Moving on to our next section where we use the non-parametric techniques to reconstruct a dark energy. We start by using a binned functional form for the dark energy described on the bottom left. The bins are connected using tan hyperbolic function with a smoothing factor of c. Here on the top left plot, I am showing the results from 3 uniform bins ranging from 0 to 2.1 and 1 additional bin to model high z behavior. The lowest redshift bin shows a deviation of more than 3 sigma and overall trend that is consistent with W0 WA. We have tested several additional binning schemes for W of z, including logarithmic binning, binning aligned with BAO traces, and even uneven binning intervals. The right panel shows the results from 3, 4, and 5 uniform bins, highlighting how constraints compare with W0 WA constraints. Lastly, we also explore a bin reconstruction of the dark energy density itself, where we allow for the priors to include the negative values, meaning we are not explicitly assuming that the rho dark energy must be positive. Interestingly, even with this flexible setup, the data consistently prefers a positive value of the rho d across all redshifts, roughly at 2 sigma level. Another non-parametric approach we use is a Gaussian process regression. Instead of assuming a specific functional form for W of z, we use GP to draw samples from the functional space. The GP is defined by a mean function, in our case lambda CDM prediction of W equals to -1, and 2 hyperparameters, sigma f that quantifies deviation away from mean function, and correlation length which sets how the smooth function are. This setup allows us to draw smooth W of z from the prior and test them against the data. You can think of it as marginalizing over family of curves rather than the parameters of your model. On the right, we show equation of state reconstruction from Gaussian process using DESI plus CMB plus union 3 and find our posterior shown in the blue, consistent with trend seen in the orange curve showing CPL constraints. Here we show how our constraints change when different combination of the data sets are considered. Using DESI plus CMB in the green, DESI plus union 3 in the orange, and all 3 datasets combined in blue. As we can see in the plot, all dataset combinations through varying degrees indicate a rise in dark energy density or equivalently W greater than -1 at low redshift. In the appendix of the paper, you can also find the detailed validation of these non-parametric methods using mock data. Each panel here shows how well different reconstruction techniques recover a known input W of z, shown as the dashed black line. Now that we have tested the robustness of these trends, what does it mean for dark energy? To answer this question, we consider 3 dark energy classes. The first class is called thawing. It describes a subclass of the quintessence model in which the scalar field is initially frozen due to the Hubble friction, but as universe expand, the field thaws away from the constant. Rather than focusing on a specific quintessence model, we use a generalized parameterization shown in the top right equation that captures this behavior. As an illustrative example, we show how dynamics of axion field translate into evolution of W of z, which is very well described by this form. It is important to note that this parameterization does not permit phantom crossings and assumes a monotonic evolution of dark energy density. The top right panel shows constraint on W of Z using DESI plus CMB plus union 3, while the bottom panel illustrates how these constraints vary with different supernovae combinations. Next, we consider emergent dark energy class. This describes scenarios where dark energy undergoes a second order phase transition. This evolution can be captured by equation on the left, where delta controls how steep the phase transition is, and Zt is a redshift for matter dark energy quality. The bottom panel shows the observation constraints on both W of Z and dark energy density from DESI alone, in combination with CMB, in combination with union 3, and all three datasets combined. This class does not fit data particularly well because the parameterization is not allowed to cross -1. The last class we explore is called the mirage. This is more of a phenomenological class where we maintain the same distance to the CMB as in the lambda CDM, but allow for the late time dynamics in the dark energy. This can be achieved by restricting the slope of W0 and WA around -3.66, and thus we create a mirage of constant W equals to -1, even though W of Z is evolving. On the right, this mirage direction shown in the magenta line aligns very well with our constraints from DESI DR1 and DESI DR2. This mirage direction can fully capture the DE phenomenology use suggested by different dataset combination with 1 degree of freedom W0 that quantifies the strength of the mirage. Within GR framework, this mirage effect is also expected to preserve the growth of cosmic structure as in lambda CDM. To test whether there is an evidence of the phantom crossing in the data, we compare how well different dark energy classes fit. This table shows improvement in the chi-square for each model relative to lambda CDM. We see that the W0WA model provides the best fit overall, improving the chi-square by 10 to 21 depending upon the supernovae combination considered. Whereas thawing models that do not allow for the phantom crossing do not perform as well as model that allows for W less than -1. To summarize, we see a strong hints of a dynamical dark energy that are very well captured by W0WA. Form independent reconstructions align very well with the trends seen in W0WA. Current data prefers a models with W crossing -1 over non-minimally coupled scalar field with rapid late time evolution. If we take data at face value, then our results suggest far more richer dark energy sector than previously expected, potentially hinting at new physics. Thank you for listening. Looking forward to hearing your comments and questions in the discussion session. You can also reach me out on Kushal Lodha at directkasi.re.kr. Thank you.